Today we are starting chapter 11, where we will be studying sound and light. These are forms of waves, and understanding how they behave will help us explain many everyday experiences, like hearing music, seeing colors, and even how mirrors work. Sound travels as compressional waves, meaning particles vibrate back and forth in the same direction as the wave moves. The speed of sound also depends on the medium it travels through. Sound moves faster in solids than in liquids, and faster in liquids than in gases because particles are closer together. Sound intensity is the amount of energy transferred by a wave through an area over time. The larger the amplitude of the wave, the more energy it carries, which means the sound is louder. Sound intensity is measured in decibels, abbreviated as lowercase d capital B. As sound travels further from its source, its intensity decreases. This is why sound becomes quieter as you move away from an object. On this slide, we are looking at the decibel scale. Louder sounds like concerts or jet engines have very high decibel levels, while quiet sounds like whispers have low decibel levels. This helps us understand how we might measure loudness, or those amplitudes, in real life. How do we perceive sound? When we hear sound, we perceive several things. Loudness comes from the intensity, pitch comes from frequency, and tone quality helps us distinguish between different sounds even if they are the same pitch. Pitch is how high or low a sound seems. It is directly related to frequency. Higher frequency means higher pitch, and lower frequency means lower pitch. For example, bass sounds have low frequency. This slide shows us the range of sound frequencies human ears can hear. Humans can typically hear between 20 and 20,000 hertz. Sounds outside this range are still waves, but we cannot detect them. You can see different mammals detect different ranges of frequencies. Ultrasonic waves have frequency above 20,000 hertz and are used in medical imaging like in ultrasounds. Infrasonic waves have frequencies below 20 hertz and can sometimes be felt as vibrations rather than being heard. The Doppler effect. The Doppler effect is a change in pitch due to the motion between the source and the observer. This happens when something is producing sound moving relative to you. In the picture, you can see the police car is moving towards the boy. Why is he smiling? Why is the girl smiling? Will someone save the boy? You guys have no idea how many outtakes I've done on this one because I can't stop laughing at this guy standing here getting hit by the waves. But I'm just going to leave this part in. As sound source moves toward you, the pitch increases. As it moves away, the pitch decreases. This man is being squished. A common example is a siren on a vehicle. Echolocation. We've already talked about this, but as you know, some animals use echolocation to determine their location. Some of those animals are bats or aquatic species like dolphins, or the most special animal, submarines. Sonar, I hardly know are. It is similar to echolocation, but is used by humans underwater, and not by humans screaming. No, in fact, these humans are inside submarines, and they're using sonar to detect objects and navigate safely. You'll notice that this boat is also using sonar, and is not, in fact, a human or a submarine. Chapter 11, Section 2, Reflection and Refraction of Light. We'll be moving on to light now that we've mastered sound. When light hits an object, it can be reflected, absorbed, or transmitted. These interactions will determine how we see an object. As previously mentioned, hold on, I've got to take care of something real quick. Don't worry about this. I don't know what that is, but I don't like looking at it. Light has three options. It can either be transmitted when it hits something, which means passed through. It can be reflected, which means bounced off, or it can be absorbed. And nothing goes through, but it will emit some light of its own. But that depends on the type of matter and the interaction that the light will have with it. Opaque. We've talked about the word opaque before. It means that light cannot pass through it. Oh no, what is it going to do? It either absorbs or reflects the light. Because of that, you can't see through them. Put your hands over your eyes. Help, I've gone blind. Help, help. Translucent. Translucent objects allow some light through, but not clearly. This image appears blurry or distorted if you're looking through it. But also, the resolution on this picture right here, not good. It's blurry, not because it's translucent, but in fact, it's just a bad picture. The green cup allows some light to go through. Transparent cup lets almost all light come through. Um, Transparent is often used as examples, but very few things are fully transparent. Just know that it means it lets almost all light through. Shapes. You've heard of them. This one's called a prism. When we have white light, it can be separated into its different wavelengths by putting that light across a prism. You'll notice this light is the rainbow. You'll also notice light, when it's separated, is the rainbow. This is because they are the same thing, and this picture is representing real life. Prisms. Ooh, you thought we were done? Not a chance. Prisms work because different wavelengths of light bend at different amounts or refract at different amounts. The shorter wavelengths, like blue and violet, bend more, while the longer wavelengths, like red, bend less. This is very important when we start talking about uh, bigger topics later in the chapter about refraction. Mirage. Mirage is that lady in Incredibles who's actually not a bad guy but just working for Syndrome. But also, Mirage is uh, an optical illusion that happens when light waves travel through air layers of different temperatures. So a lot of times you'll see these by roads because asphalt is heating up the road more than the surrounding area is being heated up because it's usually black or gray, which is absorbing more of the light, which changes the temperature around that specific area, and then it looks wavy. Chapter 11, Section 3 is all about whatever it's about to be about. You're going to know it because it's going to be what it's about. I have a feeling vampires won't like this section. Oh, hey, it's a picture of a cat. Did you know mirrors reflect light? The way they reflect light depends on the variety of mirror, whether it's a plane mirror, like the one in the picture, a concave mirror, or a convex mirror. Plane mirrors turn you into this weird looking man. Uh, hmm. All right. Well, yeah, let's talk about it. Plane mirrors are flat, like plane, like geometry, like on the plane. They produce virtual images that appear behind the mirror. The angle of incidence equals the angle of reflection, which is important for the test. You'll notice we have an angle of incidence and an angle of incidence right here. And then this man appears to be on the opposite side. And he woke up and he sees he's still just as weird looking today. Concave mirrors. Now, when you're first starting a world, you're going to want to try to get wood, get a crafting table, but then you're going to want to find a concave. That's right, concaves bend in instead of out. That'll be a different kind we'll talk about later. A concave mirror curves inward and it produces inverted images when far away and upright images when close to the focal point. If you've ever looked at the inside of a spoon, until you get close, you don't look any different other than that you're upside down. And as you get closer, you get slightly magnified and upright. We'll prove it. Take out your spoons and look at them. I'll wait. Do you have a spoon yet? Ooh, the convex mirror. Now, see, the Guardians haven't figured out why the Vex exist. We just know that they are much like a hive mind. They shop at this grocery store, Alamy.com. A convex mirror is curved outward. It makes the images upright but smaller. We use these a lot of the times for security, like in this mirror, but they can also be used in optics, which we'll talk about later. Hey, did you know optics? That means something about the eye. This one. You're looking at this video because you have them. And if you're listening to this video, I'm sorry. Imagine I'm doing a funny bit. When light enters your eye through the cornea, it bends light together. That'll pass through the pupil, which is the opening of the eye muscles, through a convex lens, which then projects a sharp image on the back of your eye at the retina, which is where different pieces will pull in different parts and send it back to the optic nerve and that back to the occipital lobe, where you will learn more about your eye. Section 4, guys, this is where it all comes together. We're probably going to learn about colors. That's about it. But to learn about colors, you also have to learn about color. Color is dependent on the wavelength of light reflected. This apple, let's say the color together. Ready? 3, 2, 1. Blue. That's right. This blue apple is blue because it absorbs all the colors except for blue. Now, if this were somehow a red apple, then it would be absorbing all the colors except for red, which it would be reflecting. Black. Black is the absence of all visible light. It absorbs all colors and reflects no light back to your eyes. It also converts to heat or thermal energy instead of visible light. I'm stuck in the void. White. The color of white is created by the full spectrum of light being directed back at your eyes. No color is absorbed at all when you see something that is white. You might be wondering, how do I see the colors? Well, you see color based off of the cones in your eye, and you see light intensity based off the rods in your eyes. The cones in your eyes are of different types. Until recently, we thought there were only 3 types of cones, but we'll get into that more. Long red cones, medium green cones, and short blue cones. They will help us see color and shapes, but without the rods helping the light, they can't work on their own. Cones work together to see color. They have 3 cones, and they cover roughly this region. You'll notice where this orange one is actually where a proposed 4th cone type exists, which we'll talk about in class, for heterochromats, which are females with a potential 4th type of cone. Rods. Rods allow you to see the intensity or lack thereof of light. So they allow you to see in dark rooms, but also in bright areas like on a snow crest hill. You will be able to see more detail if you have more rods. If you don't have a lot of rods, you have very low levels of light detection. Hello. Are you colorblind? If you are, you're likely a man and part of the 8% of men who are colorblind. Colorblind is where one of your types of cones is either not in the correct proportion or not formed at all. If you cannot see the very old internet era meme on your screen right now, you might in fact be colorblind. But Mr. Jackson, I'm an art, you might say, you little art nerd. I'm so sorry to inform you that the way we talk about pigment is different than we talk about the electromagnetic spectrum, and pigment is the material that changes color by absorbing certain wavelengths and reflecting others. We must understand filters and color mixing when we talk about pigments. Did you know the color of light is different when we're talking about primary colors And when we're talking about pigments, when we're talking about primary colors, we're talking about red, green, and blue. And those are the ones that are based around the cones of your eye. But when we're talking about the primary colors for pigments, we talk about magenta, cyan, and yellow. Why? I'm not your dad. Oh, would you look at that? I am going to tell you about them. Huh. Well, the primary colors for pigments are magenta, yellow, and cyan. When you put all of these colors together, they do not give you white. They give you black. If you ever work on a printer, like maybe I have, you'll notice that magenta, yellow, and cyan are the color types that are in a printer, whether that is a laser, inkjet, or one of those sublimation printers. And then you also need a black, because if you just add them together, it kind of clogs the head. But there are old printers that do that. At this point, you should probably have noticed that these slides are much shorter than the last chapter, and that is because you're getting faster. Please slow down. Oh no, you're almost at the end of the slide.